Hello, welcome to the first video lecture of our logic course. In this video, you will get the preparation for the practical exercise classes we have on site on campus and which we stream live via Zoom. So please watch them carefully to be prepared for the practical exercises we tell you later on in our course. Okay, so this is an introduction. So we will first see what logic is about, and we will get into touch with a very simple logic. Logic has a lot of application, but let's start with a very simple one. Let's start with an example where we have to plan a party. So the task is to find a guest list which follows certain rules or constraints, which are as follows. If two people are married, we have to invite them both or none of them. Alice is married to Bob and Cecile is married to David. Okay, then if we invite Alice, we also have to invite Cecile, but Cecile does not care if we invite Alice, but not her. Then we know that David and Eva cannot get together without having some discussions which we want to avoid. So we do not want to invite both of them, only one, and we want to invite Bob and Fred. And the question is there a solution to this problem? Can we find a consistent guest list such that all of these rules are satisfied? And now we can play around with it and find the guest list by hand. We have to consider quite some possibilities. But what we could also do is we could encode this into logic. In our case, we use Propositional Logic, which is the topic of the next 3 lectures. So if we want to make this guest list, we have to introduce statements that tell us whom to invite. We introduce so-called propositional variables, which tell us if a certain person is invited or not. So for example, we have a variable invite Alice. If it is set to true, we will invite Alice. If it's set to false, we will not invite her. And then we have so-called Boolean connective, which allows us to express the constraints. I will not go into detail how we can do this, but we here see that we have this construct saying, for example, that invite Alice has to have the same value as invite Bob. Yeah, this is this arrow in both directions here. And so if invite Alice is true, also invite Bob has to be true and vice versa. Yeah, and in a similar way we can express the other constraints. About the details we will talk in the next lecture. And having all these constraints, we can build a big conjunction of them. So we say all of them have to hold, and then we have a propositional formula, and if this propositional formula is satisfiable, then it has a solution which will give us the guest list. This is one very small example. Another example I would like to show you, and which we will also solve today, is graph coloring. Here the task is the following. We are given a graph that consists of vertices, which are also called nodes, and these vertices are connected by edges. Details on this graph coloring problem you will hear in the course Discrete Structure. In case you're doing computer science, the AI students will hear about it in their math classes. And yeah, we have this kind of structure, and mathematically we can write it like we have it here. So we have the set of vertices. In this example, we have 3 vertices, which are called A, B, and C. And we have the edges, which are pairs of vertices indicating which nodes are connected. In our case, we have an edge from A to B. It's undirected, so we do not care in which direction we go. And we have an edge from B to C, or from C to B. So the graphical representation of the graph looks like that. Yeah. Graphs are a very important concept in computer science and artificial intelligence. A lot of things are representable by graphs, and many algorithms have to deal with operations on graph, but this is not our problem. We are asking, if we're given a certain amount of colors, is there a coloring such that two connected nodes do not have the same color? So for example, if we have the two colors red and yellow, and we want to assign the colors to this graph, then A has a different color than B, and B has to have a different color than C, and what we see here is a solution for that. Looks very simple, but if the graph gets complicated, then it's not so easy to find a solution. And in the exercises you will get also in touch with using this graph coloring problem to encode Sudokus, so you can express really difficult problems with these kinds of questions. Okay, and now the idea is we have this graph coloring problem and we want to solve it. And yeah, we could implement our own tool for finding this graph coloring, but this might be a rather complicated search and we would have to spend a lot of work into finding an optimized implementation. It would be much better if we would have a tool that allows us to use it out of the box. And here the solvers come into play, which can evaluate given logical formulas and then tell us the solutions of these formulas in case they are satisfiable. And this graph coloring problem can be translated into such a formula, into such a logical formula, and then be automatically solved by a solver who gives us then the solution back. And at the end of this lecture we will see how to do this. Okay, but before we go directly into using logic for solving hard problems, what are the preliminaries? What do we have to do in order to learn logic? And learning a logic is pretty much learning languages. Yeah, so we want to have a language which is very concise, which does not have any ambiguities, where it's ensured that everybody has the same understanding of the meaning of the formula. And we can define logics of different kinds of expressiveness, which provide a lot of concepts and which are then harder to process and where it becomes harder to solve the formulas. Or we can use a more limited logic where reasoning with it, what is the main purpose of these logics, become easier. Yeah? This we can also formalize, but for now, this let's keep this these notions of hardness and expressiveness, yeah, just intuitively defined. Okay, and when we introduce a logic, we have to do several things. So first of all, we have to define a syntax. We have to say, how do the expressions of our logic look? What are elements or expressions allowed in our language? Therefore, like in a natural language, we have a set of words, which are the basic building blocks, and then we have some kind of grammar, which gives us rules for composing sentences from words and smaller sentences, such that we can build a huge formula at the end. And yeah, syntax is also important for knowing which symbols to use, and this become how to write down a formula. And there is always a trade-off between user-friendliness, so if the formula should be readable by humans or if it should be easily processable by tools. So there are standards which say how the input of the solving tools has to look like, and they are often not so user-friendly anymore. Yeah, this is always a compromise one has to take. Yeah, here I have some examples. The syntax of a language tells us how a syntactically correct or incorrect formula looks like. Here, for example, in the second line, I have a syntactically correct formula from propositional logic with symbols A and B, and A and B are connected by logical connectives or and here we have a negation, we have some parentheses for structuring. And the same formula could also be represented like that. Yeah, here we have a standard, a formula which is in the standard format of a propositional logic solver, so-called SAT solver. And here these parts here are represented by the lines. The negation symbols are the negative numbers, and the variables are the numbers. Yeah, so we have the positive numbers are the variables, and the negative numbers are the negated variables. A line is a so-called clause, and multiple lines are conjunction of clauses. But this we will discuss a bit later. Yeah, but the important point at the moment is that we can have different representations and that they serve different purposes. Yeah, and then we also know when a formula is incorrect. For example, here we have this conjunction symbol used here at the very beginning, which is wrong. Yeah, this is like in arithmetics, for example, where you also have an agreement how to use plus, multiplication, and so on. So this is the first step. We have to define how expressions in a logic look like. When we have that, we have to give them a meaning. So we have to say how to evaluate syntactically correct expressions. And what we want to have is a really concise semantics, so there should not be any ambiguities and there should not be any vagueness. Yeah, so there should be no discussion what a formula means. And therefore, we agree upon the semantics. We make it crystal clear from the beginning what a formula means, such that there is no room for discussion. So, for example, we have this formula here, and a propositional formula is an expression which is always either true or false under a certain assignment of the variables, and the truth value follows from the given assignment of the variables and the meaning we give to the disjunction, the conjunction, the negation, and so on. And this will also be topic of this lecture of today, how we define the meaning of such expressions. Yeah, and the third thing is the pragmatics. What does an expression stand for? What can we do with it? Because we do not want to have these formulas for their purpose on their own. We want to have them, to use them in application problems. We want to encode questions like, is this processor doing the right thing? Or can it happen that an error occurs? Is this program correct? What does the schedule of this planning problem look like? And so on. And in order to do so, we translate these problems into these logical formulas, as we have seen it for the graph coloring, as we have seen it for the party planning. And then we have a formula which has the symbols and logical connectives, and we interpret these variables in the specific context, like we did it, for example, with this atomic variable invite Alice. Yeah? In principle, we just have a symbol there, but we gave it the meaning that we want to invite Alice if this variable is true. Yeah, and with this, we can encode application problems and get solutions for it. And this is the one very important aspect why logic is not only interesting from a theoretical perspective. Yeah? Logic has a very long history in mathematics, in computer science. It's very foundational, but it also has a lot of exciting applications in AI and in verification. Yeah, here I have the example. The variable A could, for example, stand for invite David, B could stand for invite Eva, and then we can evaluate the formula with respect to this semantics and interpret the solution with respect to this higher level semantics, so to say. Okay, and when we have such a propositional formula, we want to perform automated reasoning and infer new knowledge. Yeah, and this is also one aspect where the power of logic comes from. So one aspect is this concise specification and description of systems. So we have no ambiguities when we use logical expressions. On the other hand, we can use them to infer new knowledge and gain new information. For this purpose, we have various sets of rules that are connected to a logic. These sets of rules are also called calculi. And these rules allow us to infer new knowledge from available knowledge. And often this reasoning is based on certain syntactical patterns. Here I have an example of such a rule, which is called modus ponens. If I know that some statement X holds, and if I have a rule which says if X holds, then also Y has to hold, then I can infer that Y has to hold as well. Yeah, and this can be used in order to make implicit knowledge of a knowledge base explicit. It may also be used to infer that a knowledge base is inconsistent, so that we have in there a certain statement such that also the negation of the statement holds. And this should not be the case, then we have a problem. And such inconsistency we can also detect with these reasoning mechanisms of logics. So here I have an example. A comes to the party, B comes to the party. If A comes to the party, then B does not come to the party. And yeah, so we have two facts saying that, and one of them says that B does come. B comes to the party. And with this inference rule, we can infer that if A comes, what is a given fact, then B does not come. But this is inconsistent to the second fact which we have here. Yeah? And things like that are very important in reasoning with logics. Okay, just a short overview what kind of logics we will do in this course. In the next 3 lectures, or starting with this lecture, we will talk about propositional logic, which is a very basic, very simple logic, but still one of the most fundamental logics in computer science, although it has quite low expressiveness and low complexity, but still it's powerful enough to solve and encode some very important problems. So this will be a topic of today and the next 2 lectures. Then we have a part on first order logic, which is extremely powerful, which has a very rich language. There is a great power of expressiveness, but reasoning with it becomes very hard. We have high complexity there. And at the end of this course, we will talk about satisfiability modulo theories, SMT, which is a compromise between expressiveness and complexity, and which is one logic that is extremely popular at the moment and widely used in industry. And we will introduce this logic or this family of logics to see how a very practical and user-friendly logical approach could look like. Yeah, this is the overview of this course, but today we will look at propositional logic. So let's talk about the syntax of propositional logic. Today I will not show you the full syntax of propositional logic, but a restricted part, a subset of the syntax of propositional logic, which is still powerful enough to capture the full language, as we will see in the next lesson. Okay, so what are the basic building blocks? So first of all, we have truth constants, which always have a fixed value. On the one hand we have true, and on the other hand we have false. True we write with this T symbol here. True is also called verum or top. And for false we write this symbol here, which is a T which has fallen on its head. And we call false also falsum or bottom. Yeah? These are two truth constants, and they always have a fixed value. Then we have the propositional variables, which we also call atom or atomic propositions. they do not have any further internal structure. Yeah, so we cannot say something more detailed about them, more fine-grained about them. These are just statements which are either true or false and which do not have any internal structure. Yeah, this will then change later on in first order logic or in SMT, where we have predicates which have which provide more information. And usually for convenience we use symbols X, Y, Z, A, B, C, P and Q to denote variables. Yeah, we will not use complicated names like invite Alice, but we will usually use one symbol for a variable, sometimes with a subscript, in order to distinguish many of them. Yeah? And then we have literals. A literal is simply a truth constant or the negation of a truth constant, meaning we take a truth constant and write this negation symbol in front of it, saying not top, not bottom. This is one kind of literal. Another kind of literal is a propositional variable or the negation of a variable. Yeah? So we have X, we have not X, we have Y, we have not Y, and so on. And for denoting literals, we use symbols L and K, also sometimes with a subscript. So we have L1, L2, L3, and so on. And we need literals, or we need the concept of literal to talk about variables or negated variables. And we do not always want to distinguish if we're talking about a variable or a negated variable. We just want to say we have a variable or a negated variable here at this point. Okay, and from literals we can then build more complex formulas, and the first additional concept we introduce is the disjunction, which combines literals to a clause. So a clause is a disjunction of literals. Here I have some examples of clauses: X or Y, X or Y or not Z, not bottom or X or A or top or not X. Yeah? So we have these three clauses here as examples of clauses. And here we also already see why it's convenient to have this notion of literal. We do not have to say now a clause is a disjunction of variables, negated variables, truth constants, negated truth constants. We just say it's a disjunction of literals. Okay? And the size of a clause is given by the number of its literals. Here we have a clause of size 2, here we have a clause of size 3, and here we have a clause of 1, 2, 3, 4, 5 literals, so it's a clause of 5 literals. Yeah, then we have some special clauses which have special names. The empty clause, which is a clause of size 0, is also written as bottom or as the empty set. We will later on see, when we discuss about the semantics, why this makes sense. So the empty clause is bottom, and or sometimes written as an empty set. Then we have the unary clause, which is a clause of size 1. They also play an important role in the reasoning. Here we have 3 examples of clauses of size 1. Not bottom is a clause of size 1. X is a clause of size 1. Not Z is a clause of size 1. Binary clauses are clauses of size 2. Ternary clauses are clauses of size 3. And yeah, for the other clauses, we usually do not have special names. Yeah? But these are the clauses that are usually of interest when doing reasoning. And we also can write a clause L1 to Ln. So here we have literals with subscript. In a more compact way, we have a big OR, and then we have an index variable saying it starts from 1 and runs until n, Li. And this big OR here stands for L1 or L2 or L3 and so on, or Ln. Yeah, this is like the sigma for the sum symbol, which you maybe remember from school. And usually we use clauses C we use symbols C, D, possibly with subscript for denoting clauses. Yeah, so uppercase C and D stand for clauses if we do not say anything else. Good. And then we want to have even more complex formulas. And we come to the following extension. A propositional formula in conjunctive normal form is a conjunction of clauses. Yeah? So we combine clauses by this conjunction symbol, and then we have a propositional formula in the so-called conjunctive normal form, which is a subset of all propositional formulas. And this is a very important subset of propositional formulas, because it can be shown that any formula of arbitrary structure can be translated into this format, and this format is very convenient for solving it. Next week we will look at arbitrary structured formulas, but there everything is a bit more complicated, and with having this simple representation we can perform reasoning much easier, and therefore it's also the standard format for most solvers we have today. Okay, here I have some examples of formulas in conjunctive normal form. We have here X, and so X or top, which is a clause, and Y or not Z, which is a clause, and not Y or not X, which is a clause. So we have 3 binary clauses in this formula here. In the second formula here we have 1 ternary clause and 1 unary clause, yeah, and so on. And here we have a clause with several running variables. This is also important to have when proving some theorem of where some statements about formulas of arbitrary size are made. Yeah, note here we have double index. First position stands for the clause, and then we have here clause 1, here we have clause n. Second index stands for the literal within the clause. Important is that we put clauses into parentheses. Also here this has some semantic reasons, which we will see later on. That's important. If we omit the clauses, the parentheses around the clauses, we will have a different formula with a different meaning, and therefore we need to make the parentheses around the clauses. Yeah. And like for the clauses, for conjunction we have also this notation with the big end. We have a big end symbol, a running variable which gives the index, and the index clauses, which is also often very convenient to have. And full formulas we usually denote by Greek symbols, for example with phi and psi, and possibly also annotated with a subscript in case we are dealing with many formulas. It's important to note that when introducing the syntax, I made a special choice what to use in this lecture. So I choose this T for true, this T flipped on the head for false, this symbol here for negation, and this symbol for disjunction and for conjunction. I also made a choice, yeah, which is a very common choice, but in the literature you might find different choices, or also in the programming languages there you have these Boolean expressions. For example, if you do a if statement, then you write a condition. There you have a logical and, a logical or, a logical not, and this is much the same as the Boolean connectives we have here, but in a different notations. And yeah, so do not get confused if a formula looks a bit different. You have to read Preliminaries, what kind of syntax is used, and then it doesn't make a difference. Also, for example, in the context of hardware design, logic plays an important role, and there they have a quite a different notation. Yeah, so don't get confused, just check which symbols are used, and then you can easily transfer your knowledge about Boolean operations to them. Okay, let's sum up for the syntax. We introduced a sublanguage of propositional logic, which is called propositional formulas in conjunctive normal form. We have formulas that are conjunction of clauses. A clause is a disjunction of literal. A literal is a negated variable or a negated truth constant, or a variable or a truth constant. And important, any formula can be translated into CNF. Now we have defined the structure of a propositional formula. We have to give it a meaning. And before we do so, let's introduce a very important concept, what we will use later on, and this is this if and only if. Yeah. So when you see an if with a double F, this is not a typo, but this is a special meaning. And what does it mean if we have a statement A is true if, with two F, standing for if and only if B is true? This means that if A is true, then it follows that also B is true. And if B is true, then also A is true. Yeah, so there is a close connection between A and B. They always have the same value. And what is very important is we can read such a statement, such an if and only if, in both directions. Yeah? If we know that A is true, then we conclude that B is true. If we know that B is true, we can conclude that A is true. Let's have a look at an example. N is an even integer. If and only if n divided by 2 has remained as 0. Yeah, this we can read in both directions. N is an even integer. Then it follows that we can divide it by 2 and get remainder 0. If we get remainder 0 when dividing integer n, then we know it's even. It is not always the case that a statement can be in both directions. It can also hold only in one direction or in 0 direction. Each of the directions has to be proven. If you do such a statement or it's a definition, then it's given that it holds. Yeah? Here I have an example of a statement that only holds in one direction. If n is larger than 2 and it is prime, then n is not an even number, so it's an odd number. Yeah? But if n is not an even number, or if n is an odd number, then we cannot conclude in the other direction that m is prime. Yeah? So this statement only holds in the one direction. If the condition is true, if n is larger than 2 and it's prime, then we can conclude that it's an odd number. And in the other direction, this is not true. Yeah? But in the following, we will often see this if and only if on the level where we describe the semantics, and also for comparing formulas and stating properties following from the semantics. Okay, but now let's go to the semantics. And let's start by a case. Let's start by the different cases in order to assign values to a formula. Okay, so if we have given a variable, then a variable can take one of two values. It can take the value true or it can take the value false. We write a 1 for true and 0 for false. And in order to make a statement about the truth value of a variable, we have a mapping that maps each variable of interest. So this is usually the variable that is in the considered formula. This mapping maps each variable of interest to such a Boolean value. Yeah? So this assignment tells us whether a variable is true or false. For example, the sun shines, yeah, is an atomic statement. This can be true or this can be false. And then based on the value we assign to this atomic statement, the more complex statements get their value. Sometimes we write an assignment not as a function but as a set of literals, or a subset of literals containing variables and negated variables. And if a variable is contained in the set, then this assignment mapping that we are considering or describing sets the variable to true. If not x is in the set, then x is set to false. Yeah, so we have this alternative notation of writing down an assignment. We can either write it down as a function, or we can write it down as a set of literals, and those variables included in this set, either negated or not negated, are assigned a specific value. And if we have n variables, there are 2 to the power of n assignment possible. This is not so hard to see. So for each variable we have 2 assignments. If we have n variables, we have 2 times 2 times 2 gives 2 to the power of n assignments. And the truth constant top is always true, and the truth constant bottom is always false. Yeah, there is no choice here. Okay, and what we have now to do is we have to define the meaning of the operators. Let's start first with the negation symbol, which is a unary connective, meaning that it has one operand, exactly one operand, and it flips the truth value of its operand. And in the way we introduce the formula, the operand of a negation is a variable. So and this we can express in terms of a truth table. So here we write down all different cases. We have one variable. This variable can be true, or this variable can be false. This is here in the first line. This variable can be true. This is here in the second line. If x is false, then not x is true. If x is true, then not x is false. And here we have some examples. If also not bottom, not false is always true. Not top is false. When we have an assignment of a variable a, and a is assigned true, then not a is false under this assignment. If variable a is false under an assignment, then not a is true under the assignment. Yeah, next we define the meaning of binary connectives. This works similar, but now we have 2 operands. And for the disjunction operator, we have the following truth table. So we have 2 literals and all different combinations. Both are false. K is true and L is false. L is true, K is false, and both are true. And then the semantics of the disjunction is defined as follows. If both L and K are false, then L or K is false. If at least one of them is true, then their disjunction is true. Yeah, so a disjunction is true if at least one operand is true. So here we have some example. A or not A is obviously always true, because either A is true or not A is true. Therefore, the disjunction of them is true. Top or A is always true. The truth value of bottom or A depends on the value of A. Yeah? Bottom cannot make this disjunction true, but if A is true, it is true. If A is false, then the disjunction is false. And now we have to describe some important properties of the disjunction. Also, like we do it with plus and multiplication in math. And these properties follow directly from the truth table. You can directly read it off. If we have a disjunction K or L, which is true, then also L or K is true. So you can swap the order and it doesn't change the true value. Yeah? And if we have two formulas, K or L and L or K, then we can also write directly that these formulas are equivalent, saying that meaning that if the one is true, also the other one is true, and vice versa. Yeah. So K or L has always the same true value as L or K. Yeah? And this can be directly read off from the truth table. Then an important property of this Boolean operators is idempotency. L or L is true if and only if L is true. Therefore, L or L is equivalent to L. Also, this can be directly checked with a truth table. Then we have associativity. If we have three literals, L1, L2, or L3, then it doesn't matter how we put the parentheses. Yeah? So it doesn't matter if you say L1 or L2 or L3, or if we say L1 or L2 or L3. I hope this is now clear from the sound how I put the parentheses, but you see it here on the slides. In any case, this is equivalent, and because of this, we can omit the parentheses and have huge clauses. Yeah, we can just put one parenthesis around a full clause, because neither the order doesn't matter nor how we put the binary parentheses. Yeah. And for this reason, we can have these huge clauses, and therefore we can also write clauses as set. So this is sometimes very convenient. This means we do not have duplicates. Literal does not occur multiple times, and the order is not important, and this follows from these properties of disjunction. And then we can use set union to add a literal to add a literal to a clause, and we can also remove a literal. We can also remove a literal from a clause by taking out the literal from the set. Yeah, so this is often very convenient, and using or interpreting clauses as sets is justified because of these properties we have just mentioned. Okay, and then we can do the truth table for a clause with n literals. So we have literal L1 to Ln, we have 2 to the power of n possibilities, and only in the case that all literals are false, the clause is false, otherwise the clause is true. Yeah? So a clause is true if and only if at least one of its literals is true. And this makes reasoning about clauses very convenient, because we immediately see, or it's very easy to see if a clause is true or not, given an assignment. Yeah, in consequence, the empty clause is always false. When we discussed the syntax, we said the empty clause can also be written as bottom, and the reason is if there is nothing in the clause, then there is nothing to be made true, and therefore if we have the empty clause, it's equivalent to bottom. Yeah, and for the conjunction, the situation is similar. The difference is that a conjunction is true if and only if both operands are true. And this is reflected as follows in the truth table. So in the first 3 lines, the conjunction of C and D is false. Only in the last line, where both C and D are true, their conjunction is true. In the examples, we have A and not A is always false. So this is a contradiction. This can never be true, because one of them, of A or not A, is one of them is always false. So therefore A and not A is false. Top and A is true if A is true. Bottom and some formula or A, doesn't matter what we write here, is always false. Yeah? Because as soon as we have one operand that is false, the whole thing is false. And if we have a formula A or B, which is true, or which is assumed to be true, and if a formula not C or D is true under some assignment, then also the conjunction A or B and not C or D is true under this respective assignment. Yeah? So the connection of two formulas that evaluate true under, which evaluate to true under some assignments give again a true formula. Yeah, again we have some properties here. Conjunction is also commutative, so order of clauses doesn't matter. It's idempotent, we can remove duplicate clauses. Associative, we can put a parenthesis in arbitrary order, and in consequence formulas in CNF can also be written as sets of sets, and this gives a very convenient data structure to implement a form for the implementation of formulas in CNF. And to add a clause C to a CNF, we can use union operator again, and to remove a clause we can also do this by taking the clause out of the set. Yeah? And again, order of clauses doesn't matter, duplicates do not matter, and yeah, so we can easily generalize conjunction from a binary operator to an Unary operator. And for the Unary definition of a conjunction, we have the following truth table. So a formula in CNF is true if and only if all of its clauses are true, which is reflected in the truth table that only in those cases when all clauses, yeah, here we have clauses in the headline, yeah, if all of the clauses are true, then the conjunction of the clause is true. And the empty CNF formula is always false. We can write therefore the empty CNF formula also as top, yeah, because there is no clause in there which can falsify the formula. Clauses are constraints, and if all constraints are true, then the formula is true. If there is no constraint that could be falsified, the formula is true. Okay, and yeah, here I have a larger example of a truth table with 3 variables. We have x, y, and z. This gives us in total 8 combinations because we have 2 to the power of 3 possibilities. Yeah, and then for calculating the truth value for each assignment, we can do it very slowly. So first we do it for x or y. X or y is only false in those cases where x and y are both false. This is only here in the first 2 lines. Otherwise, this clause is true. Then we have not set, which is simply the negation of the set variable. So we flip the value. This is reflected by the column here. And then we can assemble the 2 values we have calculated to the final result. And for example, for assignment 0, 0, 0, when all variables are set to false, the formula is false. Or here we have another assignment picked. X is set to true, y is set to false, z is set to false. Yeah? So this is an assignment which we write as a set of literals x, not y, not z. And yeah, if we perform an evaluation of the formula under this assignment, the formula evaluates to true. Yeah, so we have introduced the semantics in terms of truth tables. We can also write it more descriptive and not explicitly list all combinations. And this will be later on very important for define formulas with a more, for defining the semantics of formulas with a more complex structure. And yeah, here I have written down typical formal definition of the semantics of propositional logic. So let P be the set of atomic variables, of the propositional variables, and let L be the set of all formulas that can be constructed from those variables. Yeah? And then we are given an assignment, such a function, and we want to know which value takes the formula under this assignment. and therefore we introduce an interpretation function which is parameterized by this assignment we are given here and which maps a formula to a Boolean value. Yeah? And if the formula we are considering is top, then the value under this given assignment is 1. If the formula is bottom, then it's obviously 0. If we have a variable, yeah, then the variables interpreted according to the assignment. Yeah, so because we know which value the variable takes, and so we take simply the value from the assignment. If in the next case we have the negation of a variable or a truth constant, and this formula not P is true if and only if P evaluates to false under this assignment. So if then we have to consider the value of P and negate it. Yeah, and here it's important we have an if and only if. If P evaluates to false, then not P is true. If not P is true, then P obviously evaluates to false. Yeah. Then we need the interpretation of a clause. A clause is true if and only if there is at least one literal in this clause such that this literal evaluates to true. And finally, a formula in CNF is true if and only if all clauses of this formula evaluate to true under the assignment. Yeah? So we, in principle, have just written up in a compact way the thing we introduced with the truth table before. Yeah, and here is some more terminology. An assignment which makes a formula true is a satisfying assignment. An assignment which makes a formula false is a falsifying assignment. A satisfying assignment is also called a model of a formula. A falsifying assignment is also called a countermodel of a formula. And if we have here this formula x or y and not z, then x, y, z is a countermodel because this not z evaluates to false if z is true. But x, y, not z is a model because x and y are set to true, therefore the first clause is true, and not z is true because z is set to false, and therefore not z is true. Yeah? Since this here is a unary clause, I omitted this parenthesis, but according to the convention I made before, I should put parentheses around it. But if we have a clause of size 1, then it's okay to omit the parentheses. I should maybe mention at this point. Okay, and now we come to SAT, the Boolean satisfiability problem, which is one of the most fundamental problems in computer science and artificial intelligence, I would say. And we are dealing with the following question. We're given a propositional formula phi. Is there an assignment that satisfies phi? Yeah? This is SAT, the Boolean satisfiability problem. And for a formula in CNF, this problem is formulated as follows. Can we find an assignment to the variables occurring in the formula such that each clause contains at least one literal that is true under this assignment? And this is the satisfiability problem of propositional logic. And with this problem, when we can solve this problem, then we can also solve many other problems as well, because this problem has a lot of important properties that makes it important from a theoretical as well as from a practical side for describing and solving other problems. Yeah, and finally, I would like to show you a practical SAT solver. For this course, we use a dedicated SAT solver which has been developed for didactical purposes. This SAT solver has a very simple syntax which is very close to the syntax we use here in the lecture and is therefore very easy to use. And yeah, you can download it from this webpage here, fmv.jku/fmv.jku.at limbul. On this webpage there is also a link to a web interface, so you do not have to install it, but you can directly use it in this web interface. Otherwise, it's not a program with a GUI, but it's to be used from a console. We have binaries for Windows, Linux and Mac, but yeah, the most convenient to use is this Limbul on the go, where you have a web interface. And yeah, how do formulas in this format look like? With variables that are strings or letters, digits, and some special symbols. The negation is an exclamation mark, the disjunction symbol is this pipe, and the conjunction symbol is this and. And if we have this formula here, A or B or not C, and not A or B and C, then we can write A pipe B pipe not C, and not A pipe B and C. Yeah. So this is rather straightforward, and Limbul supports a more general language, in fact, but this we will use only next time. For now, we are focusing on these CNF formulas, yeah? But Limbul would be able to process also more advanced formulas. Yeah, practical SAT solvers, so state-of-the-art solvers, use a much simpler format. They have lines with numbers, positive or negative, as we have seen at the very beginning. And this format called Dimex is very easy to parse and to handle, but it's not so well suited for didactical purposes. Therefore, we use this format. Okay, and now I make a short demo. Here we have the Limbul web interface, and what we want to do is we do not want to perform a validity check, we want to perform a satisfiability check. Next week we will see what is this validity check, but for now let's just choose satisfiability checking, and let's enter the formula from before, A or B or not C and not A or B and C. Yeah, let's write it like that. Okay, and now when we run, and we have hopefully made no syntax error, then the solver says the formula is satisfiable, and it gives a truth assignment under which the formula evaluates to true. If we set A to false, then the second clause becomes true. If we set B to true, then the first clause becomes true, and if we set C to 1, also the last one becomes true. If we now, for example, say that also A has to be true, but B has to be false, like that, then the formula becomes unsatisfiable. So here we see that the formula is unsatisfiable. Why is this the case? C is true because of this unit clause here, A is true because of this unit clause here, and B is false because of this unit clause here, but this falsifies the second clause here. This cannot come true under this assignment. Yeah, more examples we will discuss in the exercise class. And to conclude, let's have a look at the graph coloring encoding and how we express this in SAT. So in graph coloring, the task is to assign colors of two nodes such that two connected nodes do not have the same color. And in particular, this is challenging when we have only a restricted number of colors. So if we have k colors. And now we want to express this problem in propositional logic. We are given a graph with vertices V, as I said, and E, which is also a set of edges. So like we had here in the example, we have vertices ABC and edges AB and BC. And say we want to now color each node in one of k colors such that there are no connected nodes with the same color. And how can we encode this generally in propositional logic? And later on we will have a look at an example. So for each coloring, for each node, we introduce a variable. We name the colors 1 to k, yes, to distinguish them, to make it easier. And a propositional variable v has color j is if this variable vj is true. Yeah? And now we want to formulate the constraints such that it is indeed this case, that is indeed the case that vj is true if node v has color j, and also that the constraints of the problems are reflected. So first of all, we have to say that each node has a color. Then we have to say that each node has just one color. And finally, we have to say that neighbors have a different color. And this we can encode with the propositional encoding we have here. So we do a big conjunction over all nodes. So we say for each node, and then we do a big disjunction over all colors. And this disjunction says each node has at least one color. Yeah? Because the disjunction is true if at least one of the variables is true. Yeah? Let's go here to the small example. Yeah, we have the nodes A, B, C. We have variables A1, A2, saying that variable A has color 1, or node A has color 2. Then we have the same for B and also the same for C. And the first constraint, saying that each node has a color, results in the following clauses. Node A has color 1 or color 2, node B has color 1 or color 2, and node C has color 1 or color 2. If we would have 3 colors, then we would get here 3 ternary clauses. If we would have more nodes, we would get more clauses. Yeah, so if we have more colors, the clauses would get larger. If we have more nodes, we would get more clauses. Okay, then we have to ensure that each node has just one color, and this we do by a couple of binary clauses, and we say that node V, for node V, it holds that it has not color I or not color J. Yeah? It cannot be the case that Vi and Vj are true at the same time. In our example, this means we have not A1 or not A2, not B1 or not B2, not C1 or not C2. If both, if node C, for example, would have both colors 1 and 2, then both variables C1 and C2 would be true, but then this would falsify this clause. So it cannot be the case that a node has 2 colors. And finally, the most interesting constraint, neighbors have different colors, and this works similar as this just one color constraint. As we say that it cannot be the case that 2 connected nodes, V and W, have the same color. So not Vi or not Wi. So here we now have the same index, whereas here in the just one color we have different indices. Yeah? So it cannot be that A and B have both color 1. It cannot be that A and B have both color 2. It cannot be that B and C have both color 1, and it cannot be that B and C have both color 2. And with this, we have now everything we need. We assemble all those clauses we just constructed to a full formula and with this we can hand it over to a SAT solver and solve it automatically. In the exercise class I will show you a bit more about this encoding and also show you how it looks like to solve it with a SAT solver, but let's just discuss this together and then play around with it in Limbo. Okay, that's it for now. Thank you very much for watching and see you in the exercise class.